Right now, in the space between your eyes and this screen, something is pushing. Not air, not light, not anything you were taught exists. Dark energy is tearing apart the fabric of reality at an accelerating rate, and the silence from the scientific establishment about what they've discovered is deafening. In 2011, the Nobel Prize in Physics went to 3 astronomers who proved the universe's expansion is accelerating. They expected applause. What they got was a crisis so profound that it threatens to collapse the entire framework of modern cosmology. The equations don't work. The observations contradict theory. And the implications of what dark energy actually is are so disturbing that many physicists refuse to discuss them publicly. If you want to understand why the cosmos is unraveling faster than science can explain it, keep watching, because what I'm about to reveal will fundamentally alter your perception of physical reality. Prepare yourself. We begin. The vacuum of space is not empty. This realization alone should shatter everything you believe about the universe. When you look at the night sky, you see darkness punctuated by points of light. Stars, planets, distant galaxies glowing against the void. But that darkness between celestial objects, that cosmic emptiness that seems to contain nothing, is seething with energy. Not metaphorically, literally. The quantum vacuum is boiling with virtual particles that pop into existence and annihilate within fractions of a second. Particle-antiparticle pairs appearing from pure nothingness, living for 10 to the negative 21 seconds before mutual destruction. This isn't speculation. This is verified quantum field theory, confirmed by countless experiments, including the Casimir effect, first measured by Dutch physicist Hendrik Casimir in 1948. He placed 2 uncharged metal plates impossibly close together in a vacuum and measured an attractive force between them. The force came from virtual particles in the quantum vacuum, having different energies inside and outside the narrow gap. The vacuum itself was pushing on the plates. Reality, even in its most empty state, contains intrinsic energy. This vacuum energy should be the source of dark energy. The math is simple enough. Calculate the energy density of the quantum vacuum using quantum field theory. Compare it to the energy density of dark energy required to explain cosmic acceleration. They should match, except they don't, not even remotely. The calculated vacuum energy density is 10 to the 120th power times larger than the observed dark energy density. This is not a small discrepancy. This is not a rounding error. This is the single worst prediction in the history of physics. By 120 orders of magnitude, imagine predicting someone's height as 1 meter and measuring it as 10 to the 120 meters. You would be predicting a human the size of the observable universe multiplied by itself trillions upon trillions of times. The cosmological constant problem, as physicists reluctantly call it, represents a complete breakdown of our theoretical framework. Either quantum field theory is catastrophically wrong, or general relativity is catastrophically wrong, or something unknown is canceling out the vacuum energy with impossible precision. The standard explanation you'll hear from science communicators is that we don't fully understand it yet. This is a lie of omission. We don't understand it at all, not partially, not incompletely. We have zero theoretical framework that can explain why the vacuum energy doesn't dominate the universe's energy budget. Some physicists propose that new physics at ultra-high energies somehow cancels out most of the vacuum energy through a mechanism we haven't discovered. This isn't a theory. This is wishful thinking dressed in equations. Others suggest that our universe exists in a metastable vacuum state, a false vacuum that could decay into a lower energy true vacuum at any moment, expanding outward at light speed and obliterating everything that exists. This possibility, called vacuum decay, isn't science fiction. It's a legitimate prediction of quantum field theory. And if it's happening somewhere in the universe right now, we would never see it coming. The bubble of true vacuum would hit us traveling at light speed. There would be no warning. No time to react. Just instant annihilation, as the fundamental constants of physics reset to new values incompatible with matter, atoms, or life. Dark energy was discovered by accident in 1998 when 2 independent teams studying distant supernovae found something impossible. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt, and Adam Rice. We're trying to measure how much the universe's expansion was slowing down. Gravity should be pulling everything together. The expansion that began with the Big Bang should gradually decelerate over billions of years as gravity fights against initial momentum. Every cosmological model predicted deceleration. Every theoretical framework assumed the universe was either heading toward eventual gravitational collapse or would expand forever but at decreasing rates. Both teams used Type Ia supernovae as standard candles, cosmic distance markers whose intrinsic brightness is known. By measuring how bright these stellar explosions appear from Earth, astronomers can calculate their distance with remarkable precision. By measuring their redshift, which reveals how fast they're moving away from us, astronomers can calculate the expansion rate at different epochs in cosmic history. Plot distance against velocity, and you should see expansion slowing down. Except it wasn't. The supernovae were dimmer than expected, farther away than they should be. The universe wasn't just expanding, it was accelerating, speeding up. Something was pushing space apart with increasing force. The discovery won the Nobel Prize, but it also broke physics. Because acceleration requires energy. Constant acceleration requires constant energy input. And making that acceleration increase over time requires an energy source that grows stronger as the universe expands. This defies every conservation law, every principle of thermodynamics, every intuition about how forces and energy behave. Gravity gets weaker as objects move apart. Electromagnetic forces diminish with distance. Even the strong nuclear force that holds atomic nuclei together operates over ranges of just femtometers. But dark energy apparently gets stronger, or at least maintains constant density, even as the universe expands and dilutes all other forms of energy. This is not how reality should work. The simplest explanation is Einstein's cosmological constant, a term he added to his field, equations of general relativity, in 1917, and later called his biggest blunder. Einstein introduced the constant to make his equations describe a static universe, balancing gravity's inward pull with a repulsive force pushing outward. When Edwin Hubble discovered in 1929 that the universe was expanding, Einstein abandoned the cosmological constant as unnecessary. But now it's back, resurrected as the leading explanation for dark energy. In this model, the cosmological constant represents an intrinsic energy density of space itself. Every cubic meter of vacuum contains the same amount of dark energy. As the universe expands, creating more space, it creates more dark energy. The total amount increases even as the density remains constant. This violates energy conservation in the most blatant way possible. Energy is being created from nothing as space expands. The universe is a perpetual motion machine operating on cosmic scales. The cosmological constant has a value of approximately 10 to the negative 29 grams per cc. This is incomprehensibly small. A cubic centimeter of intergalactic space, as empty as any region in the universe, contains just 10 to the negative 29 grams worth of dark energy. For comparison, air at sea level has a density of 0.0012 grams per cc. Dark energy is 10 to the 26 times less dense than air. Yet this infinitesimal energy density dominates the universe's expansion because space is so vast. Integrate that tiny density over cosmic volumes, and you get enough energy to accelerate hundreds of billions of galaxies away from each other. The total energy budget of the universe breaks down to approximately 68% dark energy, 27% dark matter, and just 5% ordinary matter and energy. Everything you've ever seen, touched, or experienced, every star and planet and gas cloud, every photon of light, makes up just 1/20th of the cosmic energy budget. And the dominant component, dark energy, has properties that make no physical sense. Dark energy has negative pressure. This concept is so counterintuitive that even physicists struggle to visualize it. Normal matter and energy have positive pressure. Compress a gas, and it pushes back. Confine electromagnetic radiation, and it exerts radiation pressure. Even the quantum vacuum, despite being empty, exerts positive pressure through the Casimir effect. But dark energy has an equation of state where pressure is negative and equal in magnitude to energy density. In technical terms, W equals -1, where W is the ratio of pressure to energy density. This means dark energy doesn't just fill space, it actively stretches space. The more space expands, creating more dark energy, the more that dark energy pushes space to expand faster. This creates a positive feedback loop, an exponential growth in the rate of cosmic expansion that will eventually rip apart every structure in the universe. Not eventually in some distant abstract future. The process is already accelerating. The rate of expansion you measure today is faster than the rate measured a billion years ago. The rate a billion years from now will be faster than today, and there is no mechanism to stop it. The acceleration began approximately 5 billion years ago, according to cosmological models. For the first 9 billion years after the Big Bang, the universe's expansion was decelerating as expected. Gravity dominated. Matter and radiation slowed the cosmic expansion. But as the universe grew larger, the density of matter and radiation decreased, diluted by increasing volume. Dark energy density remained constant. At some critical point around 5 billion years ago, dark energy density exceeded matter density and began dominating the universe's dynamics. The expansion began accelerating. The transition point is called matter-radiation equality, though in this case it's matter-dark energy equality. We live in a universe that has recently transitioned from deceleration to acceleration. If intelligent observers had evolved 10 billion years ago, they would have measured a decelerating universe and concluded gravity would eventually halt expansion or cause recollapse. They would have been catastrophically wrong. The universe would have seemed to obey different physics. This timing raises disturbing questions about cosmic coincidence. We exist at exactly the epoch when dark energy begins dominating the universe's expansion. A few billion years earlier, and dark energy would be undetectable, its effects too small to measure against the decelerating expansion driven by matter. A few billion years later, and acceleration would be so extreme that galaxy formation would be suppressed, stars would be isolated, and intelligent life might never develop. We appear to live in a narrow window of cosmic history when the universe is old enough for complex structures to form, but young enough that dark energy hasn't torn everything apart. This coincidence bothers physicists. It suggests either we're observing the universe at a special time, violating the Copernican principle that our perspective is not privileged, or there's some connection between the emergence of observers and the properties of dark energy. Both options are philosophically nauseating. The anthropic principle offers one explanation. If the cosmological constant had a significantly different value, either positive or negative, the universe would be inhospitable to life. A larger positive constant would accelerate expansion so rapidly that galaxies never form. Matter would disperse before gravity could collapse it into stars and planets. A negative constant would cause the universe to recollapse before stars could form or evolve. Only in a narrow range of cosmological constant values does the universe evolve structures complex enough to support observers. Therefore, we necessarily find ourselves in a universe with the right amount of dark energy because we couldn't exist in universes with the wrong amount. This anthropic argument is technically correct, but explanatorily empty. It's like saying we live on Earth because Earth-like planets are the only places where humans can live. True, but it doesn't explain why Earth exists, or why the universe contains planets at all. The anthropic principle feels like giving up on finding deeper explanations. String theory offers a different anthropic argument through the landscape problem. In string theory, the fundamental building blocks of reality are one-dimensional strings vibrating in 10 or 11 dimensions. The extra dimensions beyond our familiar 3 spatial dimensions are compactified, curled up at sizes too small to detect. But there are an enormous number of ways to compactify these extra dimensions. Some estimates suggest 10 to the 500 different possible vacuum states, each with different physical constants, particle masses, and cosmological constant values. Our universe exists in one of these vacuum states, with a cosmological constant that allows structure formation and observers. Other vacuum states might have different constants incompatible with life. This landscape of possible universes transforms the cosmological constant problem from "why does it have this specific value?" to "why are we surprised we're in a vacuum state that allows our existence?" Again, this is anthropic reasoning. It sidesteps the question rather than answering it. and it requires accepting the existence of 10 to the 500 unobservable universes that we can never test or detect. Some physicists hate the cosmological constant model because it requires fine-tuning. The value needs to be small enough that acceleration only recently began, but not zero. It needs to be positive for acceleration rather than negative for deceleration. It needs to have exactly the right magnitude to explain observations. Critics argue this feels arbitrary. Why this value and not some other? The response is that in a landscape of 10 to the 500 possible values, one of them will match observations. But this response assumes string theory's landscape is real, which is itself controversial. String theory has produced 0 testable predictions in 50 years of development. It remains a mathematical framework without experimental verification. Using it to explain dark energy feels like explaining one mystery with another mystery. Alternative models propose that dark energy is not a constant but a dynamic field that evolves over time. These models go by names like quintessence, K-essence, and phantom energy. Quintessence treats dark energy as a scalar field, similar to the Higgs field or hypothetical inflation field, that pervades space with energy density that changes as the field rolls down its potential energy curve. In these models, the equation of state parameter W isn't exactly -1 but varies over time. Current observations constrain W to be very close to -1, within a few percent, but don't rule out small deviations. If W is slightly greater than -1, say -0.95, dark energy density decreases very slowly over time. The acceleration would eventually slow down, perhaps even reversing in the far future. If W is slightly less than -1, say -1.05, dark energy density increases over time faster than space expands. This leads to a big rip scenario, where acceleration becomes infinite in finite time, tearing apart galaxies, stars, planets, atoms, and ultimately space-time itself. The Big Rip represents the most violent possible fate of the universe. In this scenario, dark energy density increases exponentially, driving acceleration to infinity in approximately 20 to 50 billion years, depending on the exact value of W. As acceleration intensifies, it overcomes the forces holding structures together. First, galaxy clusters get ripped apart as dark energy overpowers the gravity binding them. Individual galaxies separate, pulled by accelerating space faster than their mutual gravitational attraction can hold them. Then galaxies themselves dissolve as stars get torn from their orbital paths. Solar systems disintegrate as planets separate from their suns. Eventually, dark energy acceleration becomes so extreme that it overcomes molecular bonds, ripping apart solid matter into individual atoms. Then, atomic nuclei split as the strong nuclear force fails against dark energy's tidal effects. Finally, space-time itself develops infinite curvature and tears. The universe ends not in heat death or cold darkness, but in catastrophic destruction where even the geometric structure of reality fails. This is not metaphor. This is legitimate physics, if the equation of state parameter W is less than -1. Current observations from the Planck satellite, the Dark Energy Survey, and other projects constrain W to -1.03 plus or minus 0.03. This means W could be exactly -1, indicating a true cosmological constant, or it could be slightly less than -1, indicating phantom energy heading toward a big rip. The uncertainty in W translates to fundamental uncertainty about the universe's ultimate fate. We don't know if cosmic acceleration will continue indefinitely at its current rate, or if it will intensify until reality itself tears apart. This should terrify you. The difference between eternal expansion and catastrophic destruction comes down to measuring W to within a few percent accuracy, which is at the edge of current observational capability. Modified gravity theories offer a radical alternative. What if there's no dark energy at all? What if the accelerating expansion is actually evidence that general relativity breaks down on cosmic scales? Einstein's theory of gravity has passed every test in the solar system, every prediction for binary pulsar systems, every observation of gravitational waves from merging black holes. But these tests probe gravity at relatively small scales, planetary orbits to stellar systems. Cosmic scales are billions of light years, regions where we've never directly tested whether gravity behaves as general relativity predicts. Modified Newtonian dynamics, called MOND, was proposed to explain galaxy rotation curves without invoking dark matter. Extended to cosmological scales, theories like TeVe's attempt to explain cosmic acceleration without dark energy by modifying how gravity works across vast distances. These theories introduce new fields, or change the relationship between matter, geometry, and gravitation. They make predictions that differ from general relativity in specific, testable ways. The problem with modified gravity theories is that they tend to fail other observational tests. They might explain cosmic acceleration, but then predict incorrect gravitational lensing around galaxy clusters, or wrong predictions for the cosmic microwave background radiation's temperature fluctuations. General relativity is incredibly successful. Modifying it to fix one problem usually breaks predictions that already work. This doesn't mean modified gravity is impossible, just that it's challenging to construct theories that improve on general relativity without introducing new problems. Most physicists favor dark energy models because they preserve general relativity and only require adding an energy component to the universe's content rather than rewriting fundamental laws. But this conservatism might be misguided. If dark energy really has negative pressure and creates energy from nothing, we're already dealing with physics that violates conservation laws and thermodynamics. Is that really less radical than modifying gravity? The connection between dark energy and the vacuum catastrophe returns to haunt every explanation. Why is the observed dark energy density 120 orders of magnitude smaller than quantum field theory predicts? Supersymmetry was proposed as one solution. In supersymmetric theories, every particle has a superpartner with different spin statistics. Fermions have bosonic superpartners. Bosons have fermionic superpartners. These superpartners contribute to vacuum energy with opposite signs, potentially canceling most of the vacuum energy through precise symmetry. If supersymmetry were exact, vacuum energy would be exactly zero. But supersymmetry must be broken in our universe, because we don't observe superpartners at particle accelerator energies. The breaking mechanism introduces new contributions to vacuum energy that might leave a small residual value matching dark energy density. This sounds promising until you calculate the numbers. Even with broken supersymmetry, the predicted vacuum energy is still many orders of magnitude too large. Supersymmetry reduces the discrepancy from 120 orders of magnitude to perhaps 60 orders of magnitude. This is improvement but nowhere near solving the problem. Weinberg's anthropic bound provides a different perspective on the vacuum catastrophe. Steven Weinberg calculated in 1987 that if the cosmological constant were larger than about 100 times its observed value, galaxies wouldn't form. The accelerating expansion would prevent matter from collapsing under gravity before structures could assemble. This places an anthropic upper limit on the cosmological constant. Observers can only exist in universes where the constant is small enough for galaxy formation. Weinberg's bound was made before dark energy was discovered. When acceleration was measured in 1998, the cosmological constant turned out to be within a factor of a few of Weinberg's anthropic limit. This coincidence suggests the anthropic principle might be operating. We observe a small cosmological constant because we couldn't exist in universes with large constants. But this still doesn't explain why the constant has its specific value, or why quantum field theory predicts a value 120 orders of magnitude too large. Dark energy surveys are attempting to measure W with increasing precision to distinguish between cosmological constant models and dynamical dark energy models. The Dark Energy Spectroscopic Instrument began operations in 2021, mapping the positions and redshifts of 35 million galaxies across cosmic history. By measuring how the expansion rate changes over time, DESI constrains the equation of state parameter W at different epochs. The Vera Rubin Observatory, beginning full operations in 2024, will observe billions of galaxies and map dark energy's effects on cosmic structure formation. The European Space Agency's Euclid mission, launched in 2023 to map galaxy distributions and gravitational lensing effects with unprecedented precision. These projects aim to measure W to within 1% accuracy, potentially revealing whether dark energy is truly constant or evolving. If W deviates from -1, even slightly, it would revolutionize cosmology and eliminate the cosmological constant as an explanation. Early results from DC created shockwaves in 2024, when preliminary data suggested W might be evolving over time, deviating from exactly -1. The evidence wasn't conclusive, falling short of the statistical significance required for definitive detection, but it hinted that dark energy might be weakening as the universe ages. If confirmed, this would mean dark energy is not a cosmological constant but a dynamical field like quintessence. The implications would be profound. A weakening dark energy might eventually stop accelerating expansion, potentially allowing gravity to halt and reverse cosmic expansion billions of years from now. Or it might transition to phantom energy, crossing W equals -1 and heading toward a big rip. The uncertainty is maddening. We might be living in a universe heading toward heat death, eternal expansion, or catastrophic destruction, and we won't know which until observations improve. The coincidence problem returns in every dark energy model. Why does dark energy density approximately equal matter density at the current epoch? For most of cosmic history, matter dominated. In the far future, dark energy will dominate completely. We exist during the narrow transition period when matter and dark energy densities are comparable. This seems unlikely unless there's a physical connection between matter and dark energy. Some models propose tracking quintessence, where the scalar field's energy density tracks matter density for much of cosmic history before diverging recently. This reduces the coincidence but requires fine-tuned initial conditions or specific potential energy curves that seem arbitrary. Other models invoke symmetries or new physics that couple dark energy to matter density. But these mechanisms are speculative, lacking experimental evidence or theoretical motivation beyond solving the coincidence problem. The holographic principle offers a wildly different perspective on dark energy. Proposed by Gerard T. Hooft and developed by Leonard Susskind, the holographic principle states that the information content of a volume of space is proportional to its surface area rather than its volume. This strange property emerges from black hole thermodynamics, where entropy is proportional to the event horizon's area. If the holographic principle applies to the universe as a whole, it places limits on how much information and energy can exist in any region of space. Some researchers propose that dark energy represents the minimum energy density allowed by holographic bounds. As the universe expands, the cosmic horizon increases in area, allowing more degrees of freedom and thus more energy. Dark energy would be the holographic vacuum energy required to fill the expanding cosmic volume. This explanation connects dark energy to quantum gravity and information theory, rather than particle physics or cosmology. It's elegant but speculative, lacking clear predictions that distinguish it from other models. Vacuum decay remains the most terrifying possibility in any quantum field theory. The vacuum state of our universe might not be the true ground state, but a metastable false vacuum that could tunnel to a lower energy true vacuum at any moment. Think of a ball resting in a valley on a mountain slope. The ball is stable in the valley, but there's a deeper valley on the other side of a ridge. Normally, the ball can't reach the deeper valley because it would have to roll uphill first, requiring energy it doesn't have. But in quantum mechanics, particles can tunnel through energy barriers with some probability. The ball could spontaneously appear in the deeper valley, even without climbing the ridge. Applied to the cosmological vacuum, our current vacuum state could tunnel to a true vacuum with lower energy density. The transition would nucleate as a bubble expanding at light speed, converting false vacuum to true vacuum. Inside the bubble, the laws of physics would change. Particle masses, force strengths, even the dimensionality of space might differ. The bubble wall carries enormous energy, incinerating everything it touches. We would never see it coming. The bubble hits at light speed. One moment you exist, the next moment, nothing. Not death. Erasure from reality, as the physical laws supporting matter and consciousness cease to exist. The probability of vacuum decay depends on the shape of the scalar field potential energy curve, which we don't know. If our vacuum is truly metastable, the tunneling rate could be incredibly low, making vacuum decay unlikely over timescales longer than the universe's current age. Or the rate could be higher, with bubbles of true vacuum nucleating throughout the universe continuously. The fact that we exist suggests vacuum decay hasn't happened in our cosmic neighborhood yet. But it could happen tomorrow, or it might have happened a billion light years away yesterday. with a bubble of true vacuum expanding toward us at light speed, annihilating everything in its path. We wouldn't see it until it arrived. The universe could be full of vacuum decay bubbles right now, expanding and colliding, and we would have no way to detect them until they reach us. This is called the vacuum metastability problem, and it's one of the most unsettling predictions of quantum field theory combined with cosmology. The Higgs field mass creates additional vacuum instability concerns. Measurements from the Large Hadron Collider determine the Higgs boson mass to be approximately 125 GeV. Combined with the top quark mass, this places our universe's vacuum state in a metastable region of the Higgs potential. Calculations suggest the vacuum could decay with a half-life around 10 to the 100 years, incomprehensibly longer than the universe's current age. This seems safe, but the calculations depend on physics at energy scales we haven't tested. New particles or interactions beyond the standard model could dramatically change the stability analysis. If the vacuum is truly metastable, quantum fluctuations or high-energy events could trigger decay. A sufficiently violent process, like colliding black holes or the Big Bang itself, might have been expected to nucleate vacuum decay. The fact that we still exist suggests either the vacuum is stable, the decay rate is extraordinarily low, or we've been cosmically lucky so far. Quantum fluctuations in the early universe pose their own dark energy mystery. During cosmic inflation, the universe underwent exponential expansion driven by a scalar field called the inflaton. Inflation stretched quantum fluctuations to macroscopic scales, creating the density perturbations that later collapsed into galaxies and large-scale structure. But inflation is driven by vacuum energy with negative pressure, exactly like dark energy. The energy density during inflation was around 10 to the 80 GeV to the fourth power, incomprehensibly larger than current dark energy density. Inflation ended when the inflaton field rolled to its minimum, transitioning from false vacuum to true vacuum and releasing its energy as matter and radiation. This transition should have left residual vacuum energy, the cosmological constant, but the residual value should be comparable to the Planck scale, around 10 to the 93 GeV to the fourth power, not the tiny value we observe. Something reduced the vacuum energy by 123 orders of magnitude. We have no idea what. The multiverse interpretation of dark energy accepts that we can't explain the cosmological constant's value from first principles. Instead, it argues that a vast ensemble of universes exists with different vacuum energies. Most universes have enormous vacuum energies that either collapse immediately or expand so violently that structure never forms. A tiny fraction have small vacuum energies compatible with galaxies and observers. We necessarily find ourselves in one of the rare universes with the right properties because we couldn't exist elsewhere. This explanation requires accepting the existence of 10 to the 500 or more unobservable universes, which many physicists find unscientific. Multiverse theories make no testable predictions. They can't be falsified. They shift the question from, why does our universe have this vacuum energy, to, why does the multiverse exist? The explanatory power is questionable, but if string theory's landscape is real, the multiverse might be unavoidable. Each vacuum state in the landscape could correspond to a different universe with different physics. Eternal inflation could create infinite copies of every possible vacuum state, generating an actual multiverse rather than just a theoretical possibility. Dark energy's equation of state could change discontinuously if the universe undergoes phase transitions. Just as water transitions from ice to liquid to vapor as temperature changes, the cosmic vacuum might transition between states with different energy densities and pressures. A phase transition could suddenly change W from -1 to a different value, dramatically altering the expansion rate. Some models propose cyclic cosmologies, where the universe oscillates between phases of accelerating and decelerating expansion driven by dark energy phase transitions. In these scenarios, dark energy increases until reaching a critical density where it transitions to a different state with lower density, allowing gravity to dominate and reverse expansion. The universe contracts until reaching another critical density, where dark energy transitions back to its high-density state, driving a new expansion phase. This creates an eternally oscillating universe that avoids both the Big Rip and heat death by cycling through phases indefinitely. These models require very specific potential energy curves for the scalar field driving dark energy, curves that seem fine-tuned rather than natural. The cosmic horizon imposes fundamental limits on observation and verification. As acceleration continues, distant galaxies recede faster than light, not because they're moving through space faster than light, which relativity forbids, but because the space between us and them is expanding faster than light can cross it. Light from these galaxies becomes increasingly redshifted, stretched to longer wavelengths, dimmer and dimmer, until it fades below detection thresholds. Eventually, these galaxies cross the cosmic horizon, disappearing from observable reality entirely. Future civilizations billions of years from now will see a much emptier universe than we observe today. Most galaxies will have receded beyond the horizon. The cosmic microwave background radiation will be redshifted into undetectability. Future observers will have access to less cosmological data than we have now. They might conclude they live in a small, static universe containing only their local galaxy group. They would be wrong but unable to discover their error because the evidence has literally left observable reality. This raises a disturbing epistemological question. If future observers will have insufficient data to discover the Big Bang and cosmic expansion, are we in a similar position regarding deeper truths about reality? Could there be cosmological phenomena that existed in the past but have receded beyond our horizon? Could there be physical laws or particles that operated in earlier epochs but left no trace in the current universe? We assume we can reconstruct cosmic history from current observations, but this assumption might be naive. The accelerating expansion is actively erasing evidence, reducing the universe's information content from our perspective. We might be living in a narrow window of cosmic history when the universe is old enough for intelligent observers, but young enough that crucial cosmological evidence hasn't been destroyed by expansion. This makes the timing of our existence even more coincidental and disturbing. The arrow of time itself connects to dark energy through thermodynamics. The second law of thermodynamics states that entropy, the measure of disorder, always increases in closed systems. This increase defines time's direction. But why does entropy increase? Why does time flow forward? In the early universe, entropy was extremely low despite high temperatures. Matter and energy were in an ordered state far from thermal equilibrium. As the universe expanded and cooled, entropy increased as structures formed and evolved. Stars burn hydrogen, increasing entropy. Black holes evaporate, radiating entropy. Every process in nature increases total entropy. Eventually, the universe will reach maximum entropy, a state of thermal equilibrium where no free energy remains to do work. This is heat death, the ultimate fate of the universe in most cosmological models. But dark energy accelerates the approach to heat death by spreading matter and energy across increasingly large volumes, reducing the density and temperature until every region reaches the same cold, dark, empty state. However, dark energy might prevent true heat death by maintaining an energy density floor. Even in the infinite future, empty space will contain dark energy density. This energy can't be extracted or used because it has negative pressure and doesn't clump or concentrate. But it exists, preventing the universe from reaching absolute zero energy density. In a universe with dark energy, heat death isn't complete thermodynamic equilibrium, but a state where matter and radiation have maximally dispersed while dark energy remains. This could be called dark energy-dominated heat death, a cosmos consisting almost entirely of dark energy with occasional isolated black holes that will eventually evaporate through Hawking radiation. After 10 to the 100 years, even the largest black holes will evaporate completely. After 10 to the 120 years, matter itself will decay if protons are unstable. The universe will consist purely of dark energy, photons, neutrinos, and occasional particles created by quantum fluctuations. This is the true final state: cold, dark, empty, eternal, and accelerating. The de Sitter space geometry describes a universe dominated by dark energy. In de Sitter space, the expansion follows exponential growth, doubling in size at regular intervals. Every point recedes from every other point at speeds proportional to distance. This creates a horizon where recession velocity equals light speed. For an observer in de Sitter space, the observable universe has a finite size determined by the cosmological constant's value. Our current universe is approaching de Sitter geometry, as dark energy dominates over matter. In the far future, the universe will be almost perfectly de Sitter, with matter density becoming negligible compared to dark energy density. The horizon will stabilize at a fixed size in co-moving coordinates. Anything beyond this horizon can never affect events inside. The universe becomes causally disconnected, broken into isolated patches that can't communicate or interact. Each patch evolves independently, forever separated from others by exponentially expanding space. De Sitter space has unusual quantum properties. The horizon generates thermal radiation similar to Hawking radiation from black holes. An observer in de Sitter space detects a thermal bath of particles at temperature proportional to the cosmological constant. This is called Gibbons-Hawking radiation. It's not real radiation in the sense of coming from outside the observer, but rather an artifact of the horizon's existence, creating quantum vacuum fluctuations that appear as particles to the observer. The temperature is extraordinarily low for our universe's cosmological constant, around 10 to the negative 29 Kelvin, far below the cosmic microwave background temperature. But in the infinite future, when the microwave background has redshifted to zero temperature, Gibbons-Hawking radiation will be the only radiation present. The universe will exist in thermal equilibrium at this minimal temperature, with occasional quantum fluctuations creating particle-antiparticle pairs that immediately annihilate. The entropy of de Sitter space is finite and proportional to the horizon area. This seems paradoxical because the universe becomes infinite in size as it approaches de Sitter geometry, yet its entropy is finite. The resolution is that entropy is measured by an observer, not from a God's eye view of the entire universe. An observer can only access information within their horizon. The number of quantum states accessible to that observer is finite, proportional to horizon area, giving finite entropy. Different observers in different locations each have their own horizons and measure the same entropy for their observable patches. The total universe might have infinite entropy, but no observer can measure it, because no observer can access infinite information. This connects to the holographic principle, where information content scales with surface area rather than volume. De Sitter space provides a concrete example where holography appears necessary to understand thermodynamics. Boltzmann brains represent the most disturbing consequence of eternal de Sitter expansion. In an infinite or near-infinite universe dominated by dark energy, thermal fluctuations will occasionally create organized structures through pure chance. Given enough time, a fluctuation could spontaneously assemble a human brain complete with false memories and consciousness, appearing for a moment before dissipating back into thermal equilibrium. This is called a Boltzmann brain, named after Ludwig Boltzmann, who considered similar ideas in the context of thermodynamics. In a universe approaching de Sitter space, Boltzmann brains become more probable than ordinary evolved observers like us. The number of Boltzmann brains that randomly fluctuate into existence in the infinite future vastly exceeds the number of biological observers that evolved in the early universe. If you're a randomly selected observer in such a universe, you're statistically more likely to be a Boltzmann brain than a real human. This creates a cosmological catastrophe for model testing. If most observers in the universe are Boltzmann brains with random false memories, why should we trust our own perceptions and memories? Our observations of cosmology, our measurements of dark energy, our entire scientific framework could be false memories implanted by chance in a Boltzmann brain that exists for microseconds before thermal dissolution. This is not idle philosophical speculation, but a serious problem for cosmologies with eternal de Sitter phases. Models that produce too many Boltzmann brains are considered observationally ruled out because they predict we should be Boltzmann brains with unreliable memories, contradicting the fact that our memories and observations show consistent patterns over time. Dark energy models must carefully avoid producing eternal de Sitter expansion or find mechanisms that suppress Boltzmann brain formation. This is an active area of research with no consensus solution. The cosmic coincidence of dark energy's recent dominance might be explained by the Q catastrophe. This is the observation that the ratio of density perturbations to gravitational potential depth, denoted Q, has a value around 10 to the negative 5. This value appears fine-tuned because slight variations would dramatically affect structure formation. A larger Q would create excessive density fluctuations, causing premature black hole formation and preventing galaxy formation. A smaller Q would make fluctuations too weak for structures to form at all. The observed Q value allows galaxy formation right around the present epoch. Some researchers propose that Q is not a coincidence but determined by dark energy dynamics. If dark energy couples to the inflaton field or to matter density through some mechanism, it could set the value of Q naturally. This would explain both the structure formation coincidence and the dark energy density coincidence simultaneously. But the required coupling mechanisms are speculative, lacking theoretical motivation from fundamental physics. The swampland conjectures from string theory impose constraints on dark energy models. The swampland is the set of effective field theories that appear consistent at low energies, but can't be completed into consistent quantum gravity theories at high energies. String theorists have proposed conjectures about which low-energy theories belong to the swampland versus the landscape of valid quantum gravity theories. One swampland conjecture states that the gradient of the potential energy curve for scalar fields must exceed a certain minimum value. Applied to dark energy, this conjecture implies that a true cosmological constant with exactly zero gradient can't exist in a consistent quantum gravity theory. Dark energy must be dynamical, a rolling scalar field rather than a constant. This conjecture, if true, would rule out the cosmological constant and require quintessence or similar dynamical models. However, the swampland conjectures are derived from string theory patterns rather than proven theorems. They might be wrong. And even if correct, they don't predict the specific form of dark energy, only that it must be dynamical. Emergent gravity theories propose that space-time and gravity are not fundamental, but emerge from more basic quantum information dynamics. In these models, dark energy could be an artifact of our coarse-grained description of emergent geometry rather than a real energy component. Eric Verlinde's entropic gravity theory suggests that gravity arises from thermodynamic entropy gradients in holographic information. Dark energy in this framework emerges from the volume law behavior of entropy in regions of space. As the universe expands, entropy increases faster than area, creating apparent dark energy effects. These ideas are highly speculative and face significant technical challenges, but they represent attempts to explain dark energy as an emergent phenomenon rather than a fundamental field or constant. If gravity and space-time are emergent, dark energy might be an inevitable consequence of information theory and thermodynamics operating at the cosmological scale. The measurement problem in quantum cosmology intersects dark energy in unexpected ways. Quantum mechanics requires wave function collapse upon measurement, transitioning from superposed states to definite outcomes. But who or what measures the universe as a whole? The wave function of the universe evolves according to the Wheeler-DeWitt equation, which lacks time as a parameter. Observables in quantum cosmology are deeply problematic because there's no external observer to collapse the cosmic wave function. Dark energy might play a role in defining the measurement problem solution by creating a preferred reference frame through the cosmological horizon. The horizon defines a boundary where quantum information becomes inaccessible, potentially enforcing wave function collapse through decoherence at horizon scales. This is extremely speculative, but represents attempts to connect dark energy, quantum mechanics, and the nature of observation in cosmology. Loop quantum gravity provides an alternative quantum gravity framework that makes specific predictions about dark energy. In loop quantum gravity, space is quantized at the Planck scale into discrete units. The theory predicts corrections to general relativity that become significant at extreme densities. Some loop quantum gravity models suggest that the Big Bang was actually a big bounce, where a previous contracting universe reached maximum density and bounced into our current expanding phase. Dark energy in these models could be related to the quantum geometry's repulsive effects at high densities, providing a natural cutoff that prevents singularities and drives expansion. The bounce mechanism might explain why the current dark energy density is so small compared to Planck scale energies. It's a residual effect of quantum gravity operating during the bounce, redshifted and diluted by subsequent expansion to the tiny value we observe today. Cyclic cosmology models propose that the universe undergoes infinite cycles of expansion and contraction, with dark energy and dark matter playing alternating roles in different epochs. Paul Steinhardt and Neil Turok developed the ekpyrotic universe model, where our universe exists on a three-dimensional membrane in higher dimensional space. Collisions between branes create Big Bang events, initiating new expansion phases. Dark energy in these models might be potential energy stored in the brane tension or scalar fields that mediate brane interactions. Each cycle could have slightly different properties, with dark energy density varying between cycles. The current epoch's dark energy density would be a random selection from the range of values the cyclic process can produce. This removes the fine-tuning problem by allowing the universe infinite attempts to produce various dark energy values, with observers only existing in cycles with appropriate values. The Trans-Planckian problem affects both inflation and dark energy. During exponential expansion, quantum modes stretch from subatomic scales to macroscopic sizes. The modes that became cosmic microwave background fluctuations started smaller than the Planck length, the scale where quantum gravity effects become dominant. This is problematic because we don't have a theory of quantum gravity to describe physics at Trans-Planckian scales. The modes, evolution while smaller than the Planck length, is unknown. Modifications to quantum field theory at Planckian scales could dramatically affect the predictions for cosmic structure. Similar issues affect dark energy if it drives eternal exponential expansion. Quantum fluctuations in the far future will be stretched to Trans-Planckian scales, encountering unknown quantum gravity physics. The universe's future evolution might depend on Trans-Planckian physics we can't calculate, making long-term predictions uncertain. The information paradox connects dark energy to black hole physics through cosmological horizons. Black holes destroy information that falls past their event horizons according to classical general relativity, violating quantum mechanics. Unitarity. Hawking radiation provides a partial resolution by allowing information to escape, but the mechanism remains controversial. Dark energy creates cosmological horizons that have similar information-destroying properties. When objects recede past the horizon due to accelerating expansion, their information becomes permanently inaccessible to observers inside the horizon. This information appears destroyed from the inside perspective, creating an information paradox analogous to black holes. Some researchers propose that information is holographically encoded on the horizon surface, preserving unitarity at the cost of radical non-locality. Others suggest information is truly destroyed in cosmologies with horizons, requiring modifications to quantum mechanics or accepting that unitarity is violated in quantum gravity. Dark energy's interaction with neutrinos provides potential observational signatures. Neutrinos are the only standard model particles light enough that dark energy could significantly affect their clustering and distribution. Most matter is too massive for dark energy's effects to overcome gravity on small scales. But neutrinos, with masses around 0.1 electron volts, could have clustering suppressed by dark energy on megaparsec scales. Neutrino mass measurements from cosmological surveys combined with galaxy clustering data can constrain dark energy properties by measuring how neutrinos respond to both gravity and dark energy. This provides an independent test of dark energy models beyond distance measurements and expansion rates. Future surveys with improved sensitivity to neutrino mass could detect correlations between neutrino clustering and dark energy fluctuations if dark energy is a dynamical field rather than a constant. The quantum vacuum structure might explain dark energy if vacuum states have degenerate or nearly degenerate energies. In quantum field theory, the vacuum is the lowest energy state of all quantum fields. But there might be multiple vacuum states, with energies separated by incredibly small differences, much smaller than typical particle physics energy scales. Transitions between these nearly degenerate vacuum states could release or absorb tiny amounts of energy, creating effective dark energy through collective behavior of many vacuum transitions across cosmic volumes. This mechanism requires vacuum states with energy splittings around 10 to the negative 3 electron volts, far below any energy scale we can probe experimentally. Such fine structure in the vacuum spectrum has no theoretical motivation, but could in principle produce dark energy density matching observations. Fifth force models propose that dark energy mediates a new fundamental force that only becomes significant on cosmological scales. This force would be carried by ultralight bosons with masses around 10 to the negative 3 electron volts, giving them Compton wavelengths comparable to the cosmological horizon size. On scales smaller than their Compton wavelength, these particles produce negligible effects. But on cosmic scales, they mediate a repulsive force that accelerates expansion. The ultralight bosons would constitute dark energy, their potential energy providing the negative pressure needed for acceleration. This model explains why dark energy effects are only noticeable cosmologically, while being negligible in solar system or galactic dynamics. However, ultralight bosons face challenges from quantum field theory, as their extreme lightness requires fine-tuned protection from quantum corrections that would give them much larger masses. Chameleon fields represent another approach to screening dark energy effects on small scales while allowing them cosmologically. Chameleon scalar fields have mass that depends on environmental density. In dense environments like Earth or the solar system, the chameleon field has large effective mass, making its range very short and effects negligible. In low-density cosmic voids, the field has tiny effective mass, allowing it to mediate long-range forces that affect expansion. This density-dependent mass provides a natural screening mechanism, explaining why laboratory tests and solar system experiments don't detect dark energy effects, even though they dominate cosmologically. Chameleon models face constraints from tests of the equivalence principle and searches for fifth forces, but they remain viable if the coupling strengths and field parameters fall within allowed ranges. Massive gravity theories modify general relativity by giving the graviton a small mass. In standard general relativity, gravitons are massless, making gravity long-range and universal. If gravitons have tiny mass, gravity becomes short-range on scales comparable to the graviton's Compton wavelength. For graviton masses, around 10 to the -33 electron volts. Gravity would transition from standard behavior on solar system scales to modified behavior on cosmological scales. This modification could produce apparent acceleration without requiring dark energy as a substance. The universe would still expand according to general relativity locally, but the expansion rate would be modified by massive gravity effects cosmologically. These theories face significant theoretical challenges, as most ways of giving gravitons mass produce ghost particles or instabilities. Recent developments like DRGT massive gravity avoid some problems but remain controversial. Galilean theories introduce derivative self-interactions for scalar fields that respect Galilean symmetry in specific limits. These theories can produce accelerating cosmological expansion while satisfying local gravitational constraints. The Galilean field's derivative interactions create screening mechanisms that suppress the field's effects in high-density regions while allowing cosmological influence. Cubic and quartic Galilean terms in the field's Lagrangian produce non-trivial dynamics that can mimic dark energy effects. However, Galilean theories face tension with gravitational wave observations. The LIGO/Virgo detection of neutron star mergers in 2017 measured gravitational wave propagation speeds equal to light speed within extremely tight constraints. Many Galilean models predict different gravitational wave speeds, ruling them out observationally. Surviving models require very specific parameter choices that seem fine-tuned. The cosmic coincidence problem appears in every dark energy model. The energy densities of matter and dark energy are comparable at the current epoch, despite evolving differently over cosmic history. Matter density dilutes as the cube of the scale factor, while dark energy density remains constant or changes much more slowly. For most of history, matter dominated. In the far future, dark energy will dominate. We exist during the brief transition period, lasting perhaps a few billion years, when the densities are comparable within an order of magnitude. This coincidence requires explanation. Tracker quintessence models attempt to solve this by having the scalar field's energy density track matter density throughout most of cosmic history before diverging recently. This requires specific potential energy curves, typically exponential or power law potentials. Even tracker models don't fully solve the coincidence because the tracking mechanism must eventually break down, and the timing of breakdown occurring near the present epoch still seems special. Anthropic explanations for the coincidence observe that galaxies form most efficiently when matter density exceeds dark energy density. If dark energy dominated earlier, gravitational collapse would be suppressed, and galaxies wouldn't form. Observers require galaxies to form stars that create heavy elements necessary for rocky planets and biochemistry. Therefore, observers necessarily find themselves at epochs when matter density recently exceeded dark energy density and galaxy formation completed. This anthropic argument explains why we observe the coincidence, but doesn't explain why the universe has properties allowing the coincidence to occur. It's descriptive rather than predictive. The timing seems too precise. Galaxy formation could have completed billions of years earlier or later, with only modest changes to dark energy density. The fact that intelligent observers emerge right around the epoch when matter and dark energy densities become comparable suggests deeper connections between structure formation complexity and vacuum energy. Vacuum energy scaling relations propose that dark energy density scales with the horizon size or other cosmological parameters. If vacuum energy density equals some constant times the inverse square of the horizon radius, it would naturally have different values at different epochs. Early universe with small horizons would have high vacuum energy. Late universe with large horizons would have low vacuum energy. The current dark energy density would simply reflect the current horizon size. This mechanism explains the value's evolution, but requires understanding why vacuum energy couples to horizon size, which lacks theoretical justification. The horizon is an observer-dependent concept, not a fundamental length scale like the Planck length. Building fundamental physics that depends on observer-dependent quantities is philosophically and technically problematic. The cosmological constant's value might be determined by quantum gravity effects in the early universe. Some models propose that Planck-scale quantum fluctuations during inflation set the cosmological constant through a relaxation mechanism. The constant starts with a random large value, but quantum fluctuations during exponential expansion drive it toward smaller values through transitions between vacuum states. This relaxation continues until reaching a value small enough that inflation ends, or until quantum fluctuations become too rare to drive further transitions. The final value would depend on the duration and energy scale of inflation, potentially explaining why the cosmological constant is small compared to the Planck scale. These relaxation mechanisms are speculative and face significant technical challenges, but they represent attempts to dynamically generate the observed cosmological constant value from quantum gravity effects. Observers are biased toward measuring specific dark energy values because dark energy affects galaxy formation efficiency. If dark energy density were much larger, structures wouldn't form and observers wouldn't exist. If it were negative, the universe would recollapse before complexity develops. This biases observed values toward a narrow range compatible with structure formation and observer existence. But this bias doesn't explain why dark energy has a value within that range rather than being exactly zero. A zero cosmological constant would be natural from symmetry perspectives. A constant around 10 to the negative 120 in Planck units requires mechanisms to cancel vast contributions down to tiny residual values with 120 decimal places of precision. This is the naturalness problem, the observation that the cosmological constant's value seems incredibly fine-tuned compared to natural scales in physics. Anthropic arguments explain why it's in the general range, allowing observers, but don't explain the specific value within that range. The future of dark energy research depends on next-generation instruments measuring cosmic expansion with unprecedented precision. The Nancy Grace Roman Space Telescope, launching in the late 2020s, will survey hundreds of millions of galaxies to map dark energy's effects on structure formation and gravitational lensing. Ground-based projects like the Simons Observatory and CMBS-4 will measure cosmic microwave background polarization with exquisite sensitivity, constraining dark energy through integrated effects on photon propagation. The Square Kilometer Array Radio Telescope will map neutral hydrogen emission across cosmic history, tracing expansion rates from the dark ages through reionization to the present. These instruments will measure the equation of state parameter W to fractions of a percent accuracy and detect any evolution over time. If W deviates from -1, it would revolutionize our understanding of dark energy and eliminate the cosmological constant as an explanation. Gravitational wave cosmology provides a completely independent probe of dark energy through standard sirens. Binary black hole and neutron star mergers emit gravitational waves whose amplitude and frequency directly measure the source's distance without requiring electromagnetic observations. Combining gravitational wave distances with electromagnetic measurements of redshift from host galaxies provides Hubble constant measurements independent of the cosmic distance ladder. Future gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, we'll detect massive black hole mergers across cosmic history, mapping expansion rates from gravitational wave standard sirens alone. This electromagnetic independent measurement can't be affected by systematic errors in distance calibrations or supernova physics, providing crucial cross-checks of dark energy properties. Discrepancies between gravitational wave and electromagnetic measurements would indicate new physics or unknown systematic effects. Fundamental physics might be tested through dark energy's quantum properties. If dark energy is a scalar field, quantum fluctuations of that field should exist and potentially leave detectable signatures. These fluctuations would gravitationally lens light, creating correlations in galaxy positions or cosmic microwave background temperature maps. Detection of dark energy fluctuations would prove it's a dynamical field rather than a cosmological constant and provide information about its quantum properties. The fluctuations' spectrum and amplitude would reveal the field's mass and self-interactions, constraining theoretical models. Non-detection would suggest either dark energy is truly constant or fluctuations are suppressed by unknown mechanisms. Current surveys approach the sensitivity needed to detect fluctuations if they exist at theoretically motivated levels. The ultimate fate of cosmic structure depends critically on dark energy's evolution. If W remains exactly -1, the universe will expand exponentially forever, with galaxies receding beyond horizons and the observable universe emptying over trillions of years. If W increases toward 0, expansion could slow, potentially allowing gravitational recollapse in the far future. If W decreases below -1, the Big Rip approaches, with acceleration intensifying until space-time itself tears apart. Current observations weakly favor W being exactly -1, suggesting eternal exponential expansion. But the uncertainties allow alternatives. We don't know if the universe faces heat death, Big Rip, Big Crunch, or something else. This fundamental uncertainty about cosmic destiny stems from our incomplete understanding of dark energy. Cosmic voids, the enormous underdense regions between galaxy filaments, provide excellent laboratories for studying dark energy. In voids, matter density is very low, allowing dark energy effects to dominate more than in average regions. The expansion rate within voids differs from the cosmic average if dark energy has spatial variations or couples to matter density. Measuring void expansion through peculiar velocities or gravitational lensing can detect dark energy properties invisible in average cosmological measurements. Voids also provide clean environments for testing modified gravity theories, which predict different void expansion rates than general relativity plus dark energy. Future surveys mapping void properties across cosmic history will test whether dark energy is truly uniform or has structure correlated with matter distribution. Dark energy might not exist at all if cosmic acceleration is an observational artifact. Some researchers propose that the universe's structure on the largest scales differs from the smooth homogeneous model assumed in standard cosmology. If matter distribution is more inhomogeneous than assumed, fitting observations with homogeneous models could introduce systematic errors that mimic dark energy. For example, if we happen to live in a large, underdense region, light from distant supernovae would be dimmer than expected, not because of acceleration, but because of different expansion rates in different density regions. These inhomogeneous models face significant challenges. They must reproduce not just supernova data, but also cosmic microwave background observations, baryon acoustic oscillations, and structure formation. Most inhomogeneous models fail one or more of these tests, but the possibility that dark energy is an artifact of oversimplified modeling, rather than a real physical component, remains technically viable and deeply unsettling, because it would mean our fundamental cosmological assumptions are wrong. The relationship between dark energy and the arrow of time goes beyond thermodynamics. If dark energy density is increasing, it defines a cosmic time direction independent of entropy. The universe has lower dark energy density in the past and higher in the future if W is less than -1. This creates an arrow of time pointing from low dark energy to high dark energy. Observers would necessarily experience time flowing in this direction because consciousness and information processing require increasing entropy, which is correlated with dark energy increase in these models. This suggests deep connections between thermodynamics, consciousness, and the cosmological vacuum that we don't understand. Could the subjective experience of time's passage be fundamentally linked to dark energy's evolution? These questions venture into philosophy but might have physical content if consciousness emerges from thermodynamic processes coupled to cosmological dynamics. The vacuum catastrophe might be explained by gravitational corrections to quantum field theory. Virtual particle loops contribute to vacuum energy in standard calculations, producing the huge 120 orders of magnitude discrepancy. But these calculations ignore gravity. At the Planck scale, gravitational effects become significant and might modify vacuum energy contributions. If quantum gravity provides a cutoff mechanism that prevents virtual particles with wavelengths shorter than the Planck length from contributing to vacuum energy, the total contribution would be reduced dramatically. This gravitational cutoff could naturally produce small vacuum energy if the physics works correctly. However, we lack a complete quantum gravity theory to perform this calculation rigorously. String theory and loop quantum gravity make different predictions about Planck scale physics. Until quantum gravity is tested experimentally, we can't evaluate whether gravitational corrections solve the vacuum catastrophe. The simulation hypothesis connects to dark energy through computational complexity. If our universe is a simulation running on some hypercomputer in a higher reality, dark energy might represent a computational optimization. Simulating strong gravitational dynamics like galaxy formation is computationally expensive. Dark energy reduces the need for detailed simulation in empty regions by accelerating their expansion and reducing interaction complexity. In this view, dark energy would be a feature, not a bug, designed to make universe simulation feasible with finite computational resources. This explanation is unfalsifiable and arguably unscientific, but it's conceptually valid. A sufficiently advanced civilization running universe simulations might implement dark energy as a load-balancing mechanism. This doesn't help us predict dark energy's properties or explain its value, but it reframes the question from why does dark energy exist to why would simulation designers choose this value? Dark energy's impact on the far future of intelligence is profound and disturbing. If expansion continues accelerating, future civilizations will face increasingly isolated cosmic environments as galaxies recede beyond horizons. Long-term survival might require harvesting energy from black hole rotation or exploiting the minimal Gibbons-Hawking radiation from the cosmic horizon. Civilizations that don't develop interstellar travel before nearby galaxies recede beyond reach will be permanently confined to their local group, unable to access resources from the broader universe. Information processing and computation face fundamental limits in accelerating universes. As the cosmic horizon shrinks in co-moving coordinates, the maximum amount of information accessible to any observer decreases. This places upper limits on the total computation possible over infinite time, suggesting that intelligence cannot grow indefinitely even given eternal existence. Dark energy might impose ultimate limits on knowledge and complexity that even arbitrarily advanced civilizations can't overcome. Brain world scenarios propose that our universe is a three-dimensional membrane embedded in higher-dimensional space. Dark energy could arise from interactions between our brain and other brains, or from the geometry of the higher-dimensional bulk space. In these models, gravity propagates through the extra dimensions, becoming modified on large scales when signals have time to spread into the bulk. This modification could produce apparent acceleration without requiring dark energy as a substance. The Dvali-Gabadadze-Parati model implements this idea, predicting modifications to general relativity on scales larger than a crossover distance set by the model's parameters. Choosing the crossover distance around the cosmic horizon size reproduces dark energy effects observationally. Brain world models face significant theoretical and observational challenges, but remain viable alternatives to dark energy. Quantum entanglement on cosmological scales might connect to dark energy through holographic principles. If the universe's information content is encoded holographically on cosmic horizons, entanglement between degrees of freedom on the horizon could manifest as dark energy in the bulk. The entanglement entropy of quantum fields across horizons scales with horizon area in ways that match dark energy density calculations in some models. This deep connection between quantum information, entanglement, and cosmological energy remains poorly understood, but represents a fascinating direction where quantum mechanics, general relativity, and thermodynamics intersect. If dark energy emerges from entanglement structure, it suggests the vacuum isn't truly empty, but filled with quantum correlations connecting distant regions of space through horizon physics. The particle physics standard model provides no candidate for dark energy. Every particle and field in the standard model either has too large a mass to explain dark energy's tiny density, or contributes to vacuum energy in ways that make the vacuum catastrophe worse rather than better. This complete lack of candidates within established particle physics is troubling. Dark energy requires either entirely new particles or fields beyond the standard model, or represents something fundamentally different from particles, perhaps a geometric property of spacetime itself. This is why cosmologists often call it dark energy rather than a specific field or particle name. We genuinely don't know what it is. We only know its gravitational effects and equation of state. Future particle physics discoveries might reveal new ultralight scalars or pseudoscalars that could constitute dark energy, but no experiments currently probe the relevant mass and coupling ranges. The Axiverse scenario from string theory predicts a landscape of ultralight axion fields that could contribute to dark energy. String theory's extra dimensions can support many distinct scalar fields, each with tiny masses determined by the compactification geometry. These ultralight axions would be nearly impossible to detect directly, but could constitute dark energy if their energy densities sum appropriately. Different axion fields might have different masses and initial conditions, creating a complex multi-component dark energy that evolves over cosmic history. This scenario is rich but highly speculative, lacking experimental verification and relying on string theory being correct. It demonstrates how theoretical frameworks like string theory generate potential dark energy candidates, even though establishing whether those candidates match observations requires precise cosmological measurements currently at the edge of feasibility. Dark energy might be a transient phenomenon that exists only during specific epochs and will disappear in the future. Some models propose that the scalar field driving dark energy is slowly rolling toward a minimum where its potential energy vanishes. Once the field reaches the minimum, dark energy disappears and cosmic acceleration stops. The universe would then enter a new phase with different expansion dynamics, possibly decelerating or coasting depending on matter content. These models explain the cosmic coincidence by noting that we observe dark energy during its active phase, which might last only 10 to 20 billion years before the field reaches its minimum. Future observers billions of years from now might measure no dark energy, leading them to conclude the universe's expansion is decelerating. This time-dependent dark energy provides a natural explanation for the coincidence, but predicts specific evolution of W that future surveys can test. The cosmological constant might have discrete allowed values determined by quantum gravity. If vacuum states form a discrete spectrum rather than a continuum, the cosmological constant could only take certain specific values separated by small but finite steps. Our universe's value would be whatever discrete level is closest to allowing observer existence. This discreteness could arise from topology or geometry of extra dimensions in string theory, or from loop quantum gravity's discrete spatial structure. If the spacing between levels is around 10 to the minus 120 in Planck units, current observations couldn't distinguish discrete levels from a continuum. But future measurements with improved precision might detect staircase structure and how dark energy changes over time, revealing underlying discreteness. This would provide extraordinary evidence for quantum gravity and revolutionize our understanding of the vacuum. Dark energy's discovery represents one of the most significant observational breakthroughs in physics. Before 1998, cosmology had no evidence for vacuum energy beyond Einstein's theoretical addition and retraction of the cosmological constant. Most physicists assumed vacuum energy was exactly zero, protected by some unknown symmetry. The supernova observations showing acceleration forced physics to confront vacuum energy's existence and deal with the 120 orders of magnitude discrepancy between theory and observation. This discrepancy is so severe that it suggests a fundamental gap in our understanding of quantum field theory, general relativity, or both. Solving the cosmological constant problem might require revolutionary new physics comparable to quantum mechanics or relativity in its departure from previous frameworks. We might be approaching the limits of what current theoretical structures can explain, demanding entirely new concepts that haven't been imagined yet. The philosophical implications of dark energy push beyond physics into existentialism. If the universe will expand forever, accelerating into cold darkness where galaxies recede beyond horizons and structure breaks down, what meaning does existence have in such a cosmos? Every achievement, every civilization, every thought will eventually be erased as the universe approaches maximum entropy and minimum complexity. The heat death waiting trillions of years in the future is inevitable if dark energy continues accelerating. Even escaping to other galaxies before they recede beyond reach only delays the inevitable by astronomical but finite time. Intelligence and consciousness appear temporary phenomena that flourish briefly during a narrow epoch when matter density supports complexity before dark energy tears everything apart. This is the ultimate cosmic horror. Not sudden destruction, but gradual, inevitable dissolution into cold, dark, empty space, expanding faster than information can cross it, isolating every remaining structure until nothing can interact with anything else ever again. Human civilization exists at a cosmologically special time. We observe a universe still young enough to contain billions of galaxies within observable range. Future observers in the far future will see vastly emptier skies as dark energy pushes galaxies beyond horizons. Past observers in the early universe saw a cosmos too hot and dense for complex structures. Our epoch falls within a window lasting perhaps 20 billion years, centered on the present, when the universe is old enough for intelligence but young enough that cosmological evidence hasn't been destroyed by expansion. This temporal anthropic principle suggests that observer formation occurs preferentially near the epoch when dark energy begins dominating, but hasn't yet isolated all structures. We necessarily find ourselves at this special time because observers couldn't exist much earlier or later. But this reasoning makes the coincidence less surprising only by accepting that most of cosmic history is inhospitable to observers, with intelligence being a transient phenomenon rather an enduring feature of reality. The observational evidence for dark energy might contain systematic errors we haven't recognized. Multiple independent measurements including supernova distances, baryon acoustic oscillations, cosmic microwave background observations, and structure formation all point to dark energy or something producing similar effects. The convergence of different methods suggests the evidence is robust. But all these methods rely on assumptions about cosmic homogeneity, standard expansion dynamics, and other aspects of cosmology that might be wrong. If the universe is more inhomogeneous than assumed, or if evolution of standard candle properties over cosmic time differs from models, the evidence could be systematically biased. Extraordinary claims require extraordinary evidence, and claiming that 68% of the universe's energy is a previously unknown component with impossible properties qualifies as extraordinary. The evidence is strong, but perhaps not yet extraordinary enough to completely rule out alternatives involving modified gravity or inhomogeneous cosmology. Dark energy research continues advancing rapidly with new observations every year refining measurements and constraining models. The field has matured from initial discovery to precision measurement science. Within the next decade, observations will measure the equation of state to percent-level accuracy and detect any time evolution if it exists. These measurements will either confirm the cosmological constant or reveal dynamical behavior pointing toward new physics. Either outcome will be scientifically revolutionary. Confirming a constant would establish vacuum energy as a real physical component requiring new theoretical understanding. Detecting evolution would rule out the cosmological constant and demand identification of the scalar field driving acceleration. Both paths lead to fundamental questions about quantum gravity, the vacuum structure, and why the universe has the properties we observe. The silence from theoretical physics about dark energy is telling. Despite 25 years since discovery, no consensus theoretical framework explains dark energy from first principles. This isn't due to lack of effort, but reflects the genuine difficulty of the problem. Dark energy connects quantum field theory's deepest mysteries about vacuum energy to cosmology's largest scales. The solution might require physics beyond both current frameworks, perhaps from quantum gravity or entirely new principles. Physicists have proposed dozens of models and mechanisms, but none have achieved widespread acceptance or produced testable predictions that distinguish them from alternatives. This theoretical stalemate suggests we might be missing crucial insights, or that the problem is fundamentally harder than anything physics has previously solved. The vacuum catastrophe's 120 orders of magnitude discrepancy is so severe that solving it might require concepts as radical as quantum mechanics was to classical physics. Reality is darker and stranger than anyone imagined before dark energy's discovery. The universe isn't just expanding but accelerating, driven by energy that shouldn't exist according to quantum field theory, and appears to violate energy conservation according to thermodynamics. The dominant component of cosmic energy has properties that make no physical sense within established frameworks. We are living inside a universe we don't understand, measuring properties we can't explain, watching reality accelerate toward a future we can't predict with certainty. Dark energy represents physics, current frontier, the place where known theories break down and new principles must emerge. Whether those principles will be discovered in our lifetime or require centuries more progress remains unknown, but the observational fact of acceleration cannot be denied. Space is stretching, galaxies are receding, and dark energy is pulling apart the cosmos faster than gravity can hold it together. If you want to watch reality unravel in real time through telescopic observations of distant supernovae and cosmic expansion rates, you'll need to stay informed as new measurements arrive. This video represents current understanding based on observations through 2024, but dark energy research moves quickly. Within 5 years, new observations might revolutionize everything I've explained. That possibility is both exciting and terrifying. Exciting because we might finally understand what dark energy is. Terrifying because the answer might be more disturbing than the question. Now that you know what scientists don't want to admit publicly about dark energy's theoretical problems and observational mysteries, consider whether you prefer the comforting lie that physics has everything figured out, or the disturbing truth that 68% of the universe is made of something we can't explain. Like this video if you choose uncomfortable truth over comfortable ignorance. Subscribe for more revelations about cosmic mysteries that challenge everything you thought you knew about reality. Because dark energy is just the beginning of what physics doesn't understand about the universe you're falling through right now. The mathematics of cosmic doom are written in equations that most physicists refuse to fully acknowledge. When you solve the Friedmann equations for a universe dominated by dark energy, with W equal to -1, the scale factor grows exponentially. This is not metaphor. The mathematical solution is A equals A0 times e to the power of h times t, where h is the Hubble parameter and t is time. This exponential function means the universe doubles in size at regular intervals, currently about every 12 billion years. The expansion rate never slows. It never stops. It continues forever, growing faster in absolute terms even though the percentage rate remains constant. In 12 billion years, the universe will be twice its current size. In 24 billion years, 4 times. In 120 billion years, over 1,000 times. Every galaxy currently visible will have receded beyond the cosmic horizon, except those gravitationally bound in our local group. The observable universe will shrink to contain just the merged remnant of the Milky Way and Andromeda, a few dozen smaller galaxies, and nothing else. Empty space stretching in all directions forever. The local group's future is gravitationally determined but cosmologically isolated. The Milky Way and Andromeda are approaching each other at 110 kilometers per second, driven by mutual gravitational attraction. They will collide in approximately 4.5 billion years, their spiral structures shredding during the merger, stars scattered into new configurations, supermassive black holes spiraling together until they merge in a cataclysmic gravitational wave event. The merged galaxy, sometimes called Milkomeda or Milkdromeda, will contain roughly 1 trillion stars. Smaller galaxies in the local group, including the Triangulum galaxy and dozens of dwarf galaxies, will also merge over the next 10 to 20 billion years. These mergers are driven by gravity operating on megaparsec scales where dark energy's effects are negligible. But beyond the local group's 10 million light-year extent, dark energy dominates completely. Galaxies in the Virgo cluster, currently 50 to 60 million light-years away, are already receding faster than we can ever reach them. The recession velocity exceeds any possible spacecraft speed. Even traveling at light speed, a journey to Virgo would fail, because the space between us expands faster than light can cross it. This creates an absolute cosmological horizon, a boundary beyond which causal contact becomes impossible. Currently, The cosmological horizon sits at approximately 16 billion light-years in co-moving coordinates. Galaxies beyond this distance are receding faster than light due to space expansion. Light emitted from beyond the horizon will never reach us no matter how long we wait. As dark energy continues driving acceleration, this horizon shrinks in co-moving coordinates. Galaxies currently within the horizon will cross it in the future, disappearing from observable reality forever. The Hubble sphere, the distance where recession velocity equals light speed, currently sits at about 14 billion light-years. Beyond the Hubble sphere, space expands faster than light, but photons can still make progress toward us because they're surfing the expanding space. Eventually, they cross back inside the Hubble sphere and reach us. But in a dark energy-dominated universe, there's a second boundary called the event horizon, beyond which even this eventual arrival becomes impossible. The event horizon is what's truly causally disconnected. For a cosmological constant with W exactly equal to -1, the event horizon sits at approximately 16 billion light-years, slightly beyond the current Hubble sphere. Galaxies crossing our event horizon are leaving observable reality permanently. Their light becomes infinitely redshifted, stretched to wavelengths larger than the observable universe itself. They fade from view asymptotically, never quite disappearing but dimming exponentially until detection becomes physically impossible. This is happening right now. Every second, approximately 20,000 stars cross our cosmological event horizon and leave the observable universe forever. You will never see light emitted by these stars after they cross the boundary. They have been erased from your future light cone. This erasure is permanent and irreversible. No technology, no matter how advanced, can recover information from beyond the event horizon. It represents an absolute limitation imposed by space-time geometry and dark energy's negative pressure. The universe is literally destroying information from your perspective, reducing the total accessible knowledge even as the universe's total content might remain constant or increase. This information destruction creates profound problems for quantum mechanics. The universe's quantum state should evolve unitarily, preserving information through all transformations. But cosmological horizons appear to destroy information that crosses them, similar to black hole event horizons. The horizon complementarity principle proposed by Leonard Susskind suggests that information isn't truly destroyed, but encoded holographically on the horizon surface. An observer inside the horizon sees information falling across and disappearing. An observer at the horizon sees information spread across the surface, never quite crossing. Both descriptions are valid from their respective reference frames. This resolves the information paradox at the cost of accepting radical observer dependence in physical descriptions. What constitutes reality depends fundamentally on where you are and what you can observe. There is no God's eye view, no objective description valid for all observers. The universe fragments into causally disconnected patches, each with its own physics, its own observable content, its own evolution. The holographic principle takes this fragmentation to its logical conclusion. The maximum information content in any region of space is proportional to the surface area of that region's boundary measured in Planck units, not the volume. For a sphere of radius r, the maximum entropy is S equals A over 4 times L underscore Planck squared, where A is the area. This seems wrong. Intuitively, information should scale with volume because you can pack more information into larger volumes. But black hole thermodynamics proves that entropy scales with horizon area. The Bekenstein-Hawking entropy of a black hole equals 1/4 of the event horizon's area in Planck units. This area scaling suggests that the physics inside any volume is completely encoded on the boundary, like a hologram where three-dimensional information is stored on a two-dimensional surface. Applied cosmologically, this means the entire observable universe's information content is encoded on the cosmological horizon surface. Everything inside, every particle, every field configuration, every quantum state is a holographic projection from boundary degrees of freedom. If the holographic principle is correct, we are living inside a hologram, not metaphorically. Literally, the three-dimensional space you perceive, the depth and volume and separation between objects, is emergent from quantum information encoded on a two-dimensional surface 16 billion light-years away. You are a pattern of information on the cosmic horizon, experiencing yourself as a three-dimensional being through mechanisms we don't understand. This is not speculation. This is serious theoretical physics, motivated by quantum gravity, string theory, and black hole thermodynamics. The ADS-CFT correspondence, proven in certain theoretical contexts, demonstrates that gravitational physics in a volume is mathematically equivalent to quantum field theory on the boundary. The bulk space is literally holographic, fully described by boundary dynamics. Whether this applies to our universe's cosmological horizon remains unproven, but the mathematics suggests it might. Dark energy determines the horizon's size, so dark energy's value determines how much information can exist in the observable universe. The Bekenstein bound quantifies this information limit. For a region of radius r containing energy E, the maximum entropy is S less than or equal to 2 pi times k times r times E divided by chi times c, where k is Boltzmann's constant, chi is reduced Planck's constant, and c is light speed. This bound comes from preventing the region from collapsing into a black hole, which would have higher entropy. The cosmological horizon has radius approximately c divided by h, where h is the Hubble parameter. The energy content is the dark energy density times the volume. Calculating the Bekenstein bound for the observable universe gives a maximum entropy around 10 to the 122. This is the total information content that can exist within our cosmological horizon. Currently, the observable universe contains far less entropy, perhaps 10 to the 103 in the form of supermassive black holes and cosmic microwave background photons. But as the universe evolves, entropy increases toward the Bekenstein bound. Once the bound is reached, no further information increase is possible. The universe reaches maximum entropy, a state of complete thermodynamic equilibrium where no free energy remains for performing work or computation. But dark energy prevents complete thermal equilibrium by maintaining a minimum energy density even in empty space. The cosmological constant represents vacuum energy that cannot be extracted or utilized. It contributes to the energy content used in calculating the Bekenstein bound, but doesn't contribute usable degrees of freedom for information storage. This creates a strange situation where the universe contains energy that counts toward thermodynamic limits, but can't support structure or information processing. The final state is not zero temperature and zero energy density, but finite temperature determined by the de Sitter horizon and finite energy density from dark energy. The Gibbons-Hawking temperature of de Sitter space is T equals chi times h divided by 2 pi times k times c, where h is the Hubble parameter. For our universe's dark energy density, this temperature is approximately 10 to the negative 30 Kelvin, incomprehensibly cold but not absolute zero. This thermal bath represents quantum fluctuations at the cosmological horizon, analogous to Hawking radiation from black holes. These quantum fluctuations have disturbing implications for the far future. At temperature T, thermal fluctuations can occasionally create organized structures through random chance. The probability of creating a structure with entropy S is proportional to e to the negative s divided by k. For small entropies, this probability is not negligible over infinite time. A single particle fluctuation occurs frequently. A small molecule takes longer. A human brain takes incomprehensibly long, but given infinite time in a universe with finite temperature, every possible configuration will eventually fluctuate into existence. This includes brains, bodies, entire civilizations, appearing spontaneously from thermal noise before dissipating back into equilibrium. These are Boltzmann brains, conscious entities created by random fluctuation rather than evolution. In an eternal de Sitter universe, Boltzmann brains vastly outnumber evolved observers, because eternal time allows arbitrarily improbable fluctuations to occur arbitrarily many times. The Boltzmann brain problem destroys the reliability of observations in eternal de Sitter cosmology. If you are a random observer selected from all observers that ever exist, you are almost certainly a Boltzmann brain that fluctuated into existence with false memories, rather than a real evolved human. Your memories of the past, your observations of cosmology, your understanding of physics are all random noise that happens to be arranged into seemingly consistent patterns. This is not idle philosophy. This is a quantitative prediction of combining thermodynamics with eternal de Sitter expansion. Models that predict too many Boltzmann brains are considered observationally falsified because we appear to have consistent memories and observations extending over decades, which is incompatible with being momentary thermal fluctuations. Dark energy models must either avoid eternal de Sitter expansion or find mechanisms that suppress Boltzmann brane formation. Neither solution is satisfactory. One proposed solution is that vacuum decay will eventually occur, preventing eternal expansion by transitioning the universe to a true vacuum with different properties. If our current vacuum is metastable, quantum tunneling to a true vacuum becomes inevitable given infinite time. The tunneling rate determines when this happens. For sufficiently low tunneling rates, vacuum decay is unlikely over timescales much longer than the current universe age. But over infinite time, probability 1 ensures it eventually occurs. When a true vacuum bubble nucleates, it expands at light speed, destroying everything in its path. The bubble wall carries enormous energy, annihilating all matter and structure it encounters. Inside the bubble, physics operates according to different laws with different particle masses and force strengths determined by the true vacuum's properties. Our universe, as we know it, ceases to exist, replaced by a new universe, with potentially no matter, no atoms, no complexity. This is called the Big Slurp, or vacuum decay catastrophe. The probability of vacuum decay per unit volume per unit time is incredibly difficult to calculate because it depends on the exact shape of the scalar field potential, which we don't know. Different models predict vastly different tunneling rates. Some suggest decay is impossible because our vacuum is truly stable. Others predict decay should have already occurred many times over. The fact that we exist suggests either our vacuum is stable or metastable with low enough tunneling rate that decay hasn't happened in our cosmic neighborhood yet. But we can't be certain. Vacuum decay could nucleate in the Andromeda galaxy right now, creating a bubble expanding at light speed that will reach the Milky Way in 2.5 million years. We would have no warning. The first indication would be the bubble wall annihilating the solar system. You cannot see it coming because it travels at light speed. Light from the bubble wall arrives simultaneously with the wall itself. One moment, stars shine normally. Next moment, oblivion. Not death, but ontological destruction, as the laws of physics supporting your existence cease to be valid. Some physicists argue that vacuum decay might have already occurred many times in the universe's history. But each decay event creates a new inflationary domain that inflates into a new universe, disconnected from the parent universe. This eternal inflation scenario suggests the multiverse is constantly spawning new bubble universes through vacuum decay and inflation. Our observable universe exists inside one such bubble, a region where inflation ended and matter formed. Beyond our cosmic horizon, eternal inflation might continue, generating infinite bubble universes with different vacuum states and different physics. This eternal inflation multiverse would contain literally every possible vacuum state allowed by the landscape of string theory, or whatever fundamental theory governs reality. We necessarily find ourselves in a bubble with physics compatible with observer formation, because we couldn't exist in bubbles with different physics. This anthropic reasoning explains our universe's properties, but only by accepting that unobservable infinite universes exist with different properties. The measure problem in eternal inflation asks how to count observers across infinite multiverses. If infinitely many bubbles exist, each containing potentially infinitely many observers, how do you calculate the probability of observing any particular set of physical laws? Infinity divided by infinity is undefined. Different methods of counting observers give different predictions for which types of physics should be most common. The geometric cutoff proposal counts observers per unit spacetime volume. The causal patch proposal counts observers within past light cones of particular events. The apparent horizon cutoff counts observers per horizon volume. Each proposal gives different answers about which vacuum states should be most probable. This measure problem remains unsolved, despite decades of work. Without solving it, eternal inflation makes no quantitative predictions and cannot be tested empirically. It degenerates into unfalsifiable metaphysics despite being motivated by rigorous physics. The string theory landscape compounds these problems by predicting 10 to the 500 different vacuum states, each with different cosmological constants, particle masses, and force strengths. This enormous landscape means almost any observed properties can be explained by finding an appropriate vacuum state. The cosmological constant's value, particle masses, coupling strengths all become environmental variables rather than fundamental constants predicted from first principles. This explanatory power comes at the cost of predictability. If anything can be explained by selecting an appropriate vacuum state, the theory makes no testable predictions. Critics argue this makes string theory unscientific. Defenders argue the landscape is a prediction that our universe should be typical among observer-containing vacua, which can be tested statistically by measuring more parameters and checking whether they match typical values. But typical according to which measure? The measure problem returns. Loop quantum cosmology provides an alternative to string theory's landscape by predicting a big bounce instead of a big bang. In loop quantum gravity, space-time is quantized at the Planck scale. When matter density reaches the Planck density, quantum geometry effects create a repulsive force preventing singularity formation. The universe cannot collapse to infinite density. Instead, it bounces, transitioning from contraction to expansion without passing through a singularity. If our universe emerged from a big bounce, the current dark energy density might be a remnant of the quantum geometry effects that drove the bounce. The bounce mechanism naturally produces a tiny positive cosmological constant as residual energy from quantum gravity effects. This could explain why dark energy is so small compared to Planck scale energies. It's a redshifted diluted remnant of the bounce that occurred 13.8 billion years ago. Loop quantum cosmology makes testable predictions about the cosmic microwave background. The bounce should create specific signatures in the temperature fluctuations and polarization patterns, detectable by current and future CMB experiments. Non-detection of these signatures would falsify the bounce scenario. Detection would provide extraordinary evidence for quantum gravity and the loop quantization of spacetime. Current CMB observations show no clear bounce signatures, placing tight constraints on bounce models. The bounce must have occurred at energies close to the Planck scale, too high to leave detectable imprints on CMB modes observable today. Or the bounce mechanism is more subtle than current models predict. Either way, loop quantum cosmology remains a viable alternative framework that approaches dark energy from quantum gravity rather than particle physics. Asymptotic safety offers another quantum gravity approach to dark energy. This framework proposes that gravity becomes scale invariant at high energies, reaching a non-trivial ultraviolet fixed point where quantum corrections stop growing. If asymptotic safety is correct, quantum gravity is well defined at arbitrarily high energies without requiring extra dimensions or string theory. The cosmological constant in asymptotically safe gravity receives finite quantum corrections rather than divergent contributions. Calculations suggest the fixed-point structure might naturally produce small positive cosmological constants compatible with observations. This would solve the vacuum catastrophe by showing that quantum gravity self-regulates vacuum energy instead of producing infinite divergences. Asymptotic safety remains speculative, but recent calculations support its viability. Definitive tests require experiments at Planck scale energies, currently impossible with foreseeable technology. Causal dynamical triangulations construct spacetime from discrete building blocks, similar to approximating smooth curves with straight-line segments. In this approach, spacetime is a quantum superposition of different geometric configurations built from simplices, the simplest geometric shapes in each dimension. Tetrahedra in 3 dimensions, 4 simplices in 4 dimensions. Computer simulations sum over all possible configurations, weighted by quantum amplitudes to find the most probable, large-scale geometry. Remarkably, these simulations naturally produce 4-dimensional spacetime with 3 spatial dimensions and 1 time dimension, matching our universe without putting that structure in by hand. The emergent spacetime shows de Sitter geometry with positive cosmological constant, providing another mechanism for generating dark energy from quantum gravity. The cosmological constant's value depends on the specific discretization details and parameters, which haven't been tuned to match observations yet. But the framework's ability to produce accelerating expansion from first principles without adding dark energy by hand is suggestive. The cosmic coincidence might be explained by selection effects we haven't recognized. Observers can only exist during epochs when the universe supports complexity. Very early times are too hot and dense. Very late times after heat death are too cold and empty. The viable window for observers spans perhaps 20 billion years centered on the current epoch. Within this window, we should expect to find ourselves at a typical time, unless there are additional selection effects favoring particular moments. If observer formation is most likely when dark energy density approximately equals matter density, we would naturally find ourselves near this transition epoch. Galaxy formation requires matter to dominate so gravity can overcome pressure and radiation. But too much matter domination leads to dense, violent environments with frequent supernova sterilization. The sweet spot for life-supporting planets might occur right when dark energy begins dominating, but structure formation has already completed. This anthropic argument is stronger than typical fine-tuning arguments, because it doesn't just say observers require certain properties, but predicts observers should emerge at specific epochs, which can be tested by studying when in cosmic history complex molecules and planets first become common. The weak anthropic principle states that observed properties must be compatible with observer existence. The strong anthropic principle states that the universe must have properties allowing observers to emerge eventually. Most physicists accept the weak principle as trivially true but reject the strong principle as unprovable and potentially unscientific. But dark energy forces serious consideration of anthropic reasoning because no other framework explains its value. If the cosmological constant were 10 times larger, galaxy formation would be suppressed and observers wouldn't exist. If it were negative, the universe would recollapse before life developed. Only in the narrow range around the observed value does the universe produce galaxies, stars, planets, and potentially observers. We necessarily find ourselves in this narrow range because we couldn't exist outside it. This explanation feels like giving up on deeper understanding, but it might be correct. Perhaps some parameters are environmental variables that vary across a multiverse, and we necessarily inhabit regions with values compatible with our existence. This would be disappointing, but not wrong. The self-indication assumption in anthropic reasoning argues that you should reason as if you are a random observer selected from all observers that exist. If Model A predicts more observers than Model B, you should favor Model A because you're more likely to exist in universes with many observers. Applied to dark energy, this suggests universes with cosmological constants, allowing maximal observer production should be most probable. But what maximizes observers? Universes with zero dark energy might produce more galaxies but collapse eventually, limiting total observer moments. Universes with small positive dark energy produce fewer galaxies but exist eternally, potentially creating more observers over infinite time. Until we understand how to count observers across time and space, self-indication reasoning remains ambiguous. The self-sampling assumption says you should reason as if you are a random observer selected from all actually existing observers, not all possible observers. This eliminates hypothetical observers in other universes and focuses on actual observers in our universe. But if the multiverse is real, other observers actually exist even if unobservable, making the distinction unclear. Doomsday arguments use anthropic reasoning to estimate humanity's future duration. The basic argument notes that if you are a random human, selected from all humans who ever live, you're most likely to exist in the middle of human history, not at the very beginning. Since about 100 billion humans have lived so far, you should expect roughly 100 billion more in the future, suggesting humanity has perhaps a few thousand more years. This seems wrong because it ignores that future populations might be much larger or smaller than past populations. The argument fails if technological civilization leads to vastly expanded populations in space or if it leads to near-term extinction. But the logic is uncomfortably sound. If human history spans millions of years and trillions of individuals, finding yourself among the first 100 billion would be incredibly unlikely. The fact that you exist early in human history suggests either the total population stays small or duration stays short. Neither option is comforting. Applied to observing dark energy, the doomsday argument suggests we're observing the universe at a typical time for observers, which might be late in cosmic history rather than early, if most observers exist after dark energy begins dominating, but before it completely isolates all structures. The Fermi paradox connects to dark energy through the question of why we don't observe alien civilizations. If life is common, intelligent life should have evolved millions of years before Earth in older star systems. Those civilizations would have had time to expand across the galaxy or even beyond. We should see evidence of their presence in megastructures, communications, or artificial signatures in astrophysical data. We see nothing. Dark energy provides one explanation. Perhaps technological civilizations inevitably discovered dark energy's implications and realized the universe is dying. This cosmic nihilism might suppress expansion and development once civilizations understand their ultimate doom. If every civilization discovers that cosmic acceleration will eventually destroy all structure and erase all their achievements, they might lose motivation for expansion or even continuation. This is called the Great Filter, a mechanism preventing civilizations from becoming visible on cosmic scales. Dark energy could be a late filter, affecting civilizations after they develop astronomy and cosmology but before they expand significantly. Alternatively, dark energy might motivate civilizations to focus on inward development rather than outward expansion. If the observable universe will shrink to just the local group in the far future, expanding beyond your local group becomes pointless. Colonizing distant galaxies is wasted effort because they'll recede beyond reach anyway. Resources are better spent developing technologies to survive in a dark energy-dominated universe than spreading across a cosmos that's being torn apart. This could explain why we don't see galaxy-spanning civilizations. They exist but remain confined to their local groups, invisible to us because intergalactic colonization is cosmologically futile. This argument assumes civilizations last long enough to reach technological maturity, but don't last the billions of years required to expand between galaxies, which seems pessimistic but might be realistic, given nuclear weapons, climate change, artificial intelligence, and other existential risks facing humanity currently. The grabby aliens hypothesis suggests that if expansionist civilizations exist, they expand at significant fractions of light speed, consuming resources and transforming galaxies as they spread. These grabby aliens would create visible signatures in galaxy modifications or energy usage patterns. The fact that we don't observe such signatures suggests either we're early among civilizations in the galaxy, or grabby aliens are rare or non-existent. Dark energy complicates this picture because even grabby aliens can't expand faster than dark energy pushes galaxies apart. The maximum extent of any civilization's expansion is limited by the cosmological horizon. Grabby aliens that started expanding a billion years ago would have colonized perhaps 1% of the observable universe before dark energy effects become limiting. Most of the universe remains permanently beyond their reach. This places absolute limits on how grabby any civilization can be, making the absence of visible aliens less surprising. The transcension hypothesis proposes that advanced civilizations focus inward, developing increasingly dense computational substrates rather than expanding outward. A civilization might convert its home star system into a maximally efficient computer, achieving more computational power in one solar system than a galaxy-spanning civilization could achieve by spreading thinly. This inward focus makes civilizations invisible to external observers because they're not generating waste heat or electromagnetic signals while maximizing internal complexity. Dark energy supports the transcension hypothesis by making outward expansion ultimately futile, while inward development faces no cosmological limits. Building denser computers, more efficient energy harvesting, and deeper virtual realities can continue even as the observable universe empties. A transcended civilization might achieve godlike capabilities within its local volume while remaining undetectable from outside. The simulation argument takes transcension to its limit. If civilizations can build computers sufficient to simulate universes containing conscious observers, and if they choose to run such simulations, then simulated universes vastly outnumber base reality. If you are a random observer, you're most likely in a simulation rather than base reality. This conclusion follows from simple arithmetic. One base universe could run millions or billions of simulations. Those simulations could run their own simulations recursively. The number of simulated observers exceeds base reality observers by enormous factors. Therefore, you're probably simulated. Dark energy affects this argument because simulating a universe with dark energy is computationally cheaper than simulating one without. Dark energy reduces the need to simulate distant regions in detail because they recede beyond horizons and stop interacting. The simulator can reduce computational resources spent on regions beyond the simulated observer's horizon without creating detectable artifacts. This makes dark energy a feature optimizing simulation efficiency rather than a bug to explain. If we are in a simulation, Dark energy might be adjustable by the simulators. They could change its value at any time, instantly altering the expansion rate and disrupting cosmology. The fact that cosmological observations show consistent patterns over decades suggests either we're not in a simulation or the simulators maintain consistent parameters. But maybe they don't care about consistency and occasionally adjust parameters for their own purposes. We would interpret such adjustments as anomalous observations or unexpected discoveries, never suspecting external manipulation. This is unfalsifiable and arguably not physics, but remains logically consistent with observations. The simulation hypothesis can explain literally any observation by invoking simulator choices, making it empirically empty, but is psychologically disturbing because it undermines confidence in the reality of physical laws. Maybe dark energy doesn't reflect fundamental physics, but merely the simulator's choice of parameters for this particular simulation. The demiurge argument extends simulation reasoning to metaphysics. Perhaps our universe was created by an entity with finite power operating within a larger cosmos. This demiurge chose our universe's parameters, including the cosmological constant, based on its own preferences or limitations. The parameters don't reflect deeper laws, but merely the demiurge's decisions or constraints it faced when creating our universe. This concept originates in Gnosticism but maps onto simulation arguments and modern physics surprisingly well. Replace demiurge with simulation designer, and the arguments are identical. The demiurge framework explains fine-tuning by invoking intentional design rather than random selection from a multiverse. But it fails to explain why the demiurge exists or where it came from, simply pushing the mystery one level deeper. Still, it remains conceptually possible that our universe's properties reflect design choices by a creator operating within a larger reality. Rejecting all anthropic and simulation arguments leaves us with the brute fact of dark energy's existence and value, unexplained by current physics. This is the most scientifically conservative position. We observe dark energy accelerating cosmic expansion. We don't understand why it has its specific value. We have no theory predicting that value from first principles. This is simply the current state of knowledge. Admitting ignorance is scientifically honest but psychologically unsatisfying. Humans crave explanations and patterns. Accepting that dark energy's value might be a random environmental variable, or a demiurge's choice, or a simulator's parameter, feels like giving up on understanding. But understanding might not always be possible. Some facts might be brute facts with no deeper explanation. The cosmological constant might be one such fact, a boundary condition on our universe not derivable from any deeper principle. This possibility is depressing, but arguably realistic. Dark energy represents a crisis point, where observation outpaces theory so severely that physics fragments into competing speculative frameworks with no clear empirical resolution. String theory's landscape, loop quantum gravity's bounces, asymptotic safety's fixed points, simulation arguments, and anthropic multiverse reasoning all attempt to explain dark energy, but none achieve consensus or experimental verification. This theoretical disarray is unusual in modern physics. Previous crises like the ultraviolet catastrophe or Mercury's orbital precession had clear experimental signatures pointing toward specific theoretical resolutions. Dark energy provides precise observations, but those observations don't point uniquely toward any theoretical framework. Multiple incompatible theories can accommodate the data, leaving theory selection criteria unclear. Do you prioritize mathematical elegance, minimal assumptions, predictive power, or consonance with other physics? Different criteria favor different theories. The cosmological constant's value might be fundamentally unpredictable, determinable only by measurement, not calculation. Some physical quantities work this way. The electron's mass cannot be calculated from first principles in the standard model. It's a free parameter determined by measuring electrons. The same might apply to the cosmological constant. No theoretical framework might ever predict its value, because it's not determined by fundamental laws but is simply one of the universe's boundary conditions. If this is true, measuring dark energy more precisely won't help understand it more deeply. We'll know its value to arbitrary precision, but remain forever ignorant of why it has that value. This would be scientifically frustrating, but might reflect actual limitations on human knowledge about the cosmos. The anthropic landscape picture, where the cosmological constant is an environmental variable, suggests that asking why does it have this value is like asking why is Earth exactly 93 million miles from the Sun? Earth's orbital radius isn't predicted from fundamental physics. It's an environmental fact determined by the solar system's formation history. Similarly, the cosmological constant might be determined by our universe's formation history, or position in the string landscape, or random fluctuations during eternal inflation. The question why this value has no deep answer beyond that's how it turned out in this particular universe. Other universes or other cosmic regions have different values. We observe our local value because we exist here. This answer satisfies anthropic reasoning, but frustrates those seeking unified theories, predicting all observable parameters from first principles. Future observations could reveal dark energy's time dependence, distinguishing cosmological constant from quintessence. If W deviates from exactly -1 or evolves over time, it would revolutionize cosmology by proving dark energy is dynamical. The specific form of time dependence would constrain scalar field potentials and coupling strengths, potentially pointing towards specific theoretical frameworks. If W crosses -1 from above to below, phantom energy is confirmed and the Big Rip becomes inevitable. This would give humanity perhaps 20 to 50 billion years to either escape the universe somehow or accept oblivion. Neither option is comforting. Escaping requires technologies beyond current physics, possibly requiring understanding quantum gravity or accessing other universes. Accepting oblivion means civilization's achievements, humanity's existence, and consciousness itself are temporary phenomena that will be erased when acceleration tears apart atoms. This is the darkest timeline, where dark energy grows stronger until reality itself cannot withstand the strain. Alternatively, if W remains exactly -1 within measurement precision, the cosmological constant is confirmed as the simplest explanation. This would focus theoretical effort on explaining why the constant has its specific value, likely requiring quantum gravity breakthroughs or accepting anthropic multiverse reasoning. The vacuum catastrophe would remain the greatest unsolved problem in theoretical physics. Explaining why the calculated vacuum energy exceeds observed dark energy by 120 orders of magnitude would become the central question driving quantum gravity research. Solving it might require entirely new physical principles, comparable to the revolution quantum mechanics brought to classical physics. We might be in the early stages of another conceptual revolution that will transform our understanding as profoundly as quantum mechanics did in the early 20th century. If W is found to be greater than -1, dark energy might be decaying, getting weaker over time. The universe's acceleration might slow and eventually stop, possibly reversing if dark energy becomes negative. This would lead to a big crunch, where gravitational attraction eventually halts expansion and reverses it, causing all galaxies to fall back together. The universe would contract, heating up as matter compresses, eventually reaching temperatures and densities comparable to the Big Bang. This might destroy all structure, or might lead to a big bounce starting a new expansion cycle. Cyclic cosmologies, where the universe oscillates between expansion and contraction, require dark energy that changes sign over time, transitioning from negative to positive and back. Such behavior has no clear theoretical motivation, but remains mathematically possible. Observations constraining W over time will test whether our universe might be cyclic or whether it faces irreversible expansion. The energy conditions in general relativity constrain which kinds of matter and energy can exist. The weak energy condition requires that energy density is non-negative in all reference frames. The strong energy condition requires that gravity is always attractive. Dark energy violates the strong energy condition because its negative pressure creates repulsive gravitational effects. But it satisfies the weak energy condition because its energy density is positive. Phantom energy with W less than -1 violates even the weak energy condition in some reference frames, suggesting it might be impossible or lead to causality violations and instabilities. General relativity allows such violations mathematically, but their physical realizability remains controversial. Phantom energy might require quantum effects or modifications to general relativity that prevent problems classical solutions would create. Wormholes and warp drives also require negative energy densities to function, suggesting connections between dark energy physics and exotic propulsion concepts. If dark energy provides a natural source of negative pressure distributed throughout space, perhaps it could be concentrated or manipulated to create stable wormholes or warp bubbles, enabling faster-than-light travel. This speculation far exceeds current physics capabilities, but the existence of dark energy proves negative pressure exists in nature, making exotic space-time configurations less impossible than previously thought. No one knows how to manipulate dark energy or concentrate its effects locally. Such technology would require understanding dark energy's fundamental nature, which we lack. But in principle, a civilization that fully understands dark energy might harness it for technologies that seem magical by current standards. Dark energy's discovery timeline shows how rapidly cosmology can be revolutionized by new observations. Before 1998, most cosmologists assumed the cosmological constant was zero, and the universe's expansion was decelerating. The 1998 supernova results showing acceleration were so unexpected that they were initially doubted and required independent confirmation from the second supernova team before acceptance. Within 5 years, cosmic microwave background observations and large-scale structure surveys confirmed acceleration through independent methods. Within a decade, dark energy became the dominant energy component in the standard cosmological model lambda-CDM. This rapid acceptance reflects the strength of converging evidence from multiple independent observations. When different measurement techniques using different physics all point to the same conclusion, that conclusion becomes difficult to deny, even if theoretically uncomfortable. Lambda-CDM is now the standard cosmological model, incorporating a cosmological constant lambda and cold dark matter CDM as the universe's dominant energy components. Only 5% is ordinary matter and radiation. The model successfully explains cosmic microwave background temperature fluctuations, baryon acoustic oscillations, galaxy clustering, weak gravitational lensing, supernova distances, and structure formation over cosmic history. This convergence of evidence makes lambda-CDM extremely robust empirically, despite its theoretical problems. The model's predictive success suggests it captures essential truths about the universe, even if the physical interpretation of dark energy remains mysterious. Lambda-CDM might be an effective theory, accurately describing observations without reflecting fundamental physics, similar to how thermodynamics accurately describes gases without requiring knowledge of atoms and molecules. The effective field theory approach treats dark energy as a phenomenological description without committing to specific microphysics. Dark energy is parameterized by its equation of state and sound speed, with observations constraining these parameters. Different microscopic theories like quintessence, k-essence, or modifications to gravity produce different predictions for these effective parameters. By measuring the parameters precisely, observations can distinguish between broad classes of theories without needing complete theoretical understanding. This pragmatic approach has proven successful in particle physics, where effective field theories describe low-energy phenomena while remaining agnostic about high-energy completions. Applying the same methodology to cosmology allows progress even without solving fundamental theoretical problems. The cosmological parameter space is explored through Markov chain Monte Carlo methods combining multiple datasets. Planck satellite cosmic microwave background data constrains early universe parameters. Baryon acoustic oscillation measurements from galaxy surveys constrain mid-universe expansion. Supernova distance measurements constrain late-time acceleration. Weak lensing measures structure growth rates. Combining all datasets produces tight constraints on cosmological parameters, including the Hubble constant, matter density, dark energy density, and equation of state. Current constraints place W at -1.03, with uncertainty around 0.03, consistent with a cosmological constant but not excluding dynamical dark energy. Future surveys will reduce uncertainties by factors of several, potentially detecting W's time evolution if it exists, or confirming constant dark energy with much higher confidence. The Hubble tension adds another layer of mystery to dark energy discussions. Local measurements using distance ladder methods calibrated by Cepheid variable stars and type Ia supernovae give Hubble constant values around 73 kilometers per second per megaparsec. Global measurements from cosmic microwave background, assuming lambda-CDM, give values around 67 kilometers per second per megaparsec. This 9% discrepancy persists despite increasing precision in both measurements and now exceeds 5 sigma statistical significance. The tension might indicate systematic errors in one or both measurements, or it might signal new physics. Early dark energy models propose that additional dark energy components existed in the early universe and decayed away, affecting cosmic microwave background predictions while leaving late-time expansion unchanged. This would reconcile the measurements if the early dark energy parameters are chosen appropriately, but such models seem contrived, adding parameters specifically to solve the tension without independent motivation. Modified gravity theories also attempt to resolve the Hubble tension by changing expansion rates at specific epochs. But modifying gravity to fix the Hubble tension often breaks other successful lambda CDM predictions, creating new tensions elsewhere. The fact that changing cosmological parameters in lambda CDM to match local Hubble measurements destroys agreement with cosmic microwave background observations suggests the model is highly constrained. It's not easy to tweak lambda CDM to accommodate discordant observations without breaking what works. This might indicate the model is wrong despite its many successes, or it might indicate the measurements contain unrecognized systematics. Resolving the Hubble tension is one of the highest priorities in current cosmology, because the resolution will either validate lambda CDM or reveal new physics. Whatever dark energy actually is, its existence forces humanity to confront cosmic futility on scales that dwarf human comprehension. Every human achievement, every thought, every emotion, every relationship, every civilization will eventually be erased as the universe expands into cold darkness. The stars will burn out, black holes will evaporate, matter itself might decay. And throughout all of this, dark energy will continue pushing space apart, accelerating expansion, destroying structure, reducing complexity, driving the universe toward maximum entropy and minimum information. Nothing you do matters on cosmic scales. Your existence is a statistical fluctuation, a temporary arrangement of particles that appeared briefly during a narrow epoch when the universe supported complexity before dark energy tears everything apart. This is the final truth about dark energy that scientists don't want to acknowledge publicly. It's not just a physics problem, it's an existential horror. The universe is not designed for life or consciousness, it's a quantum fluctuation that briefly allowed structure before reverting to featureless expansion. You are an accident. Humanity is an accident. Every thought you've ever had will be erased. Every memory destroyed. Every relationship ended, not by death, but by the cosmological constant driving everything you've ever known beyond the light horizon, where it cannot affect you or anything you care about ever again. If you've made it this far, you understand something most people refuse to accept. The cosmos is indifferent to your existence. Dark energy will erase every trace of human civilization. There is no escape, no afterlife, no permanence. Just temporary patterns in quantum fields that briefly achieved self-awareness before dissipating into the void. Like this video if you choose to face cosmic horror with open eyes rather than comforting delusions. Subscribe for more revelations about the universe's darkest secrets. Because dark energy is killing reality, and the silence from those who know tells you everything about how disturbing the truth really is.